Hello, this video is for Module 2 Part 1 and will include the various elements of conducting a statistical hypothesis test. Alright, let's go ahead and get started. A hypothesis test is a structured analytical procedure used to evaluate the amount of evidence, or lack thereof, for a research question. At the heart of a hypothesis test is the identification of likely versus unlikely outcomes. A hypothesis test also uses probabilities so that the decision being made can be done in a consistent manner. The first step in conducting a hypothesis test is the writing or identification of the research question. We will discuss three examples here, or three case studies that we've considered previously. The gender discrimination case study. The research question or question of interest for that case study was, is there evidence to suggest gender discrimination against females in the hiring of faculty at the University of Texas at Dallas? The staring example. The research question for that example was, is there evidence to say that the woman in the study has the ability to correctly identify when somebody's staring at her? And then the ear infection example, the research question there was, is there evidence to say that there's a difference in the duration of fluid in the middle ear between the breastfed and bottle-fed babies? The research question determines what type of statistical analysis is appropriate. A precise and clearly stated research question is of the utmost importance when conducting a test. Okay, a couple of additional definitions. The first, scope of inference. The scope of inference is to whom the study outcomes or the conclusions will apply. Second definition here is parameter. The parameter is a numerical value being tested in a statistical hypothesis test. The parameter is usually identified by a Greek character, and we've been using pi to denote that parameter previously, and we'll continue to do so here. So let's identify the scope of inference and parameter for each of the case studies considered. So the scope of inference for the gender discrimination. That would be the women who were seeking a faculty position within the Arts and Humanities Division at the University of Texas at Dallas. So that's whom we wish to make decisions about in our investigation. The parameter for the gender discrimination case study is just the probability of a female being hired in that division under a situation of no discrimination. The parameter value for the gender discrimination example was that 38.3%. In the staring case study, the scope of inference is just that single woman in the video. So we've identified just that woman. We obtained measurements from just that woman. So our scope of inference is just that one woman in the video. The parameter here is the probability that the woman in this study could correctly identify when being stared at under a situation of no ability. So the parameter value for that case study was set at 50-50, or pi was equal to 50%. How about the scope of inference for the ear infection example? Well, that study was done on babies that were either breastfed or bottle-fed. It is difficult to determine exactly which babies would be considered within the scope of inference for this case study, because we don't have additional information about how the researchers identified the babies to be placed into that study. For example, did these babies come from a particular medical clinic? Or from a particular geographic region within a city, maybe? We don't have that additional information about where these babies came from, which makes it difficult to appropriately describe the scope of inference. The parameter value for the ear infection example is simply the probability that a breastfed baby would do better than a bottle-fed baby in those head-to-head comparisons that were done. Again, under a situation of no difference. So that's another 50-50 example. So it is nice when our question of interest identifies or gives an indication of what the scope of inference is. And oftentimes it does. How about the formation of a testable hypothesis? This is one of the most difficult elements of conducting a test. That is to translate the research question into a hypothesis that can be evaluated using probabilities. A statistical hypothesis has two components, a null and alternative hypothesis. Let's first talk about the null hypothesis. The null hypothesis, which is denoted by an H naught, is how we say that, is what the outcome from the study is being compared against. The null hypothesis determines how the reference distribution is going to be set up. The other is the alternative hypothesis. The alternative hypothesis, denoted by an HA, is a restatement of the research question. The alternative hypothesis is a confirmation or endorsement of the research question. So let's take the research questions from our 3 case studies and translate that into those formal hypothesis statements, the H naught and the HA. So let's look at the gender discrimination. The research question, is there evidence to suggest gender discrimination against females in the hiring of faculty at the University of Texas at Dallas? Again, that's within that division of arts and sciences. The H naught is going to be that the hiring is fair. Okay, so that's what we want to compare our data against. So if we go back up here and look at the definition of the null hypothesis, it is what the outcome from your study is going to be compared against. So we're going to compare our data against a situation that the hiring was fair. So the null hypothesis here is going to be the hiring is fair. And that is that the probability of a female being hired is at that 38.3%. The alternative, again, is just a restatement of the research question. So the alternative here would be that the hiring is biased against females. In particular, the probability that a female would be hired is less than that 38.3%. Way over here on the right is how we would write that null and alternative hypothesis with the parameter value. So here I have it stated in words, and over here in the far right column we have it stated with just the parameter. So the H naught is that parameter, which again is the probability that a female is going to be hired under a fair situation. That's that 38.3%. The alternative is where our research question goes, and there we believe that the female rate was less than that 38.3%. Or that we had discrimination taking place against females. And that's represented in the HA over here in the right column. For the ear infection, the research question was, is there evidence to say there is a difference in the duration of fluid in the middle ear between the breastfed and bottle-fed babies? So again, we're going to compare our data against a situation of there being no difference. So the null hypothesis is going to be there is no difference in the duration of fluid in the middle ear between the breastfed and bottle-fed babies. That statement would be the parameter is equal to 50%. So that's a 50-50 example. The pi would be equal to 50% in the null hypothesis. The HA is suggesting that there is a difference. So that means that parameter value is going to be different than 50%. Which is represented here in the right column as well. The next step then is obtaining the reference distribution. And we've been doing that for the previous examples. But we would obtain that reference distribution under the H naught, or under the null hypothesis. So for the gender discrimination, that's going to be again the situation of fair hiring. Under the staring, it's going to be the situation of no ability. So that value from the H naught, 38.3%, is what we were using in our reference distribution app. For the ear infection example, we have parameters equal to 50% in the null hypothesis, not equal to 50% in the alternative hypothesis. Again, what we're putting in for the probability of success, or that pi value on that reference distribution app, is just that 50%. Now, the reference distribution app also requires us to identify the number of trials. For the gender discrimination, that was 48. For staring, that was 20. And for the ear infection, that was 23. I'll let you go ahead and read the comments here. There are some situations that are not testable. So there are some types of research questions that we cannot evaluate using a statistical hypothesis test. For example, version B here, this is for the ear infection. So version B of the research question is there evidence to say that there's no difference in the duration of fluid? So the original version was asking whether or not there was a difference. Version B here is suggesting that there is no difference. I would set up my null hypothesis in that situation of pi not equal to 50%. Remember, my research question goes in the alternative hypothesis. So here I would have the alternative hypothesis would be that there's no difference, or a 50-50 situation. So my null hypothesis would have to be that there is a difference here. Now, I cannot easily evaluate my data against a situation of a difference, because there's all sorts of different ways that I can have, or there's all sorts of different ways that I can be different. So the reason version B is not valid is that it is not possible to set up a unique reference distribution so that the data can be compared against. The reference distribution must be constructed under the situation of H0, and when H0 contains an inequality, there are several possibilities for setting up the reference distribution. For example, pi equal 0.55 would work, because that's not equal to 50%. A pi value of 0.83 would work to set up my reference distribution, because that's not equal to 50%. Or a pi of 0.6235, that would also work, because that's not equal to 50%. So we don't have any information about which of these reference distributions should I be comparing my data against. And in fact, all three of those might be equally probable to choose under the H0. So we don't have a single unique reference distribution that can be built in a situation or in a hypothesis like this. And for that reason, we cannot do a statistical test for version B. So the graph that we've been building and constructing, I've been calling it a reference distribution. Here's the formal definition of a reference distribution. It's simply a graph that is used to measure and evaluate the amount of evidence data provides for a research question. This distribution can be obtained through theoretical means or via a simulation model. We've been using a simulation model up to this point, and we will switch to a theoretical model in a couple of parts, and a little bit in the future. Sorry. So the reference distributions are simply the distributions that we get from our simulation models. Okay, how do we make a formal decision via the outlier rule? So we have been using the outlier rule somewhat informally up to this point, and here I will include more details about that outlier rule. So we determine statistical significance. 1 in 20 is the standard by which statistical significance is determined. So in 1 in 20 is that 5% level. It's hard to overstate how ingrained that 5% level is, not just in statistics, but just in research in general. Everybody uses that 5% as the gold standard when determining statistical significance. So another element that I need to worry about when I'm evaluating the statistical evidence is which end of the distribution that we care about. Again, we've informally talked about that through the previous case studies. I'll just remind you of 3 of the case studies here. So the gender discrimination. Again, the research question, is there evidence to suggest gender discrimination against females in the hiring of faculty at the University of Texas at Dallas? The end of the distribution that I care about there is the left end of the distribution, because that would indicate evidence of discrimination against females. Having too few females on this number line would indicate discrimination. Which end of the distribution that I'm interested in is determined by the research question. So we need to go back to the research question to identify which end of the distribution is of interest. For the staring example, the research question is there evidence to say that the woman in the study has the ability to correctly identify when someone's staring at her? Well, if she does have the ability, then she's going to get most of the selections correct. So the upper end of that distribution is going to be evidence for ability. For the ear infection, the question was, is there evidence to say that there is discrimination? Is there evidence to say there is a difference in the duration of fluid in the middle ear? That's going to be a 2-sided one. As we talked about before, if I was too low on that number line, that would indicate that bottle fed would be better. Or if I'm too high on that number line, that would indicate that breastfed babies would be doing better. So the left side or the right side or both sides is just identified as the type of the test. So the type of the test is either left-tailed, right-tailed, or two-tailed. Now to make our formal decision, all I need to do is just identify whether or not the outcome lies in the bottom 5%, the top 5%, or the outside 5%. So for a one-tailed left analysis, we'd want to be in the bottom 5%. For a one-tailed right analysis, we'd want to be in the top 5%. And for a two-tailed analysis or two-tailed test, we'd want to be in the outside 5%. So again, if the outcome from the study falls on that bottom, top, or outside 5%, then we can say the data provides enough statistical evidence for the research question. If it does not fall in that bottom 5%, top 5%, or outside 5%, then we must conclude that the data does not provide enough statistical evidence. So again, in the gender discrimination case, the 5% outlier rule was applied to the reference distribution, and it was determined that 12 and less would be considered unlikely. So for the gender discrimination case, my number line went from 0 to 48. The distribution was 38.3% of the way up. My study outcome for that particular case was, for the arts and humanities division, was 14. And that bottom 5% would be from 12 and anything below 12. Now 14 does not sit in that bottom 5%. So the formal decision for this case study was that the outcome from the study does not fall in the bottom 5% of the reference distribution. Therefore, the statistical decision would be that the data does not provide enough evidence for the research question. So quite simply, all we need to do is just identify whether or not the study outcome falls in that bottom 5%. Of course, this is a one-tailed left test. If we consider the Parolee discrimination case, so let's go back to the Parolee discrimination case. Again, this was presented, I think, in part 3 of module 1. Here, the bottom 5% was at, I think it was 28 or below. So it was determined that an outcome of 28 and less would be considered unlikely. Therefore, 28 is the appropriate cutoff for the bottom 5% of the distribution. There were a total of 24 Native Americans paroled during that time period of the study, and we can see that 24 does indeed sit in that bottom 5%. So the formal decision for this example is that the data does provide enough statistical evidence for the research question. So for the Native American parolee example, we do get to say that Native Americans were being discriminated against because the study outcome here falls in that bottom 5% of the distribution. In contrast, in the gender discrimination example, 14 does not fall in that bottom 5%, so we do not have enough evidence to suggest that there is gender discrimination taking place. So that's how we make a decision when we are using the outlier rule. Next, we are going to talk about the more common way of making a decision. So modern technology has permitted us to use an alternative method for making a decision about a research question. This alternative method is referred to as a p-value approach. So in section 2.1.6 here, we're going to be making a formal decision with a p-value. So what is the definition of a p-value? A p-value is a probability of observing an outcome as extreme or more extreme than the outcome from the study. And this p-value is computed from my reference distribution. So the p here stands for a probability. So therefore, a p-value is going to be between 0 and 1. When we say as extreme or more extreme, that includes the outcomes that would provide as much or even more support for the research question. So when determining the p-value, again, I need to clearly understand what the research question is, and I need to identify which side of the distribution provides evidence for the research question. So let's look at the staring example. Recall that the research question was, is there evidence to say that the woman in the study has the ability to correctly identify when somebody's staring at her? The reference distribution is set up with a specification of sample size 20, the parameter value of 50%, and the actual number correct was 14. So in the staring example, she had 14 out of the 20 correct. The first thing I need to do before computing the p-value is understand what outcomes from this reference distribution would be considered as extreme or more extreme than the study outcome. Again, when we're identifying those outcomes, we need the outcomes that would provide as much or more support for the research question. So 14 would be as extreme, I guess. 15 would be more extreme than 14 and provides additional evidence for the research question. 16 would also be more extreme than 14. 17, 18, 19, 20. All the values to the right of 14 would be more extreme than 14 and would provide evidence for the research question. So when we're computing the p-value, I need to estimate the probability of obtaining a 14, a 15, a 16, a 17, an 18, a 19, or a 20 from this reference distribution. And I do that by just simply counting the number of dots that are as extreme or more extreme than the outcome from my study, divided by the total number of dots. So here on this reference distribution that I've obtained, let's suppose that I obtained 200 repeated outcomes. So the number of repeated outcomes here is 200. Sorry about that. The number of repeated outcomes is 200. So what I need to do to obtain the p-value is just count how many dots are at 14, 15, 16, 17, 18, 19, or 20. So if I do that, there's going to be 15 dots down here in that region. Those are identified just by the red dots. So there's 15 dots that are at 14 or bigger, divided by the total number of dots. So I put 200 dots on this graph. So the p-value is simply going to be 15 divided by 200, which is 0.075. What is the interpretation of this p-value? Well, there is a 7.5% chance that the woman will get 16 or more correct. 14 or more correct. Let me start over there. There is a 7.5% chance that the woman will get 14 or more correct under a situation of having no ability to identify when somebody's staring at her. So again, this reference distribution is representing the no ability. So what's the chance that a woman will get 14 or more correct under that situation? And that's about 7.5%. The outcome from this study, or 14, would be located in the top 7.5% of the reference distribution. If the p-value is very, very, very small, so let's suppose that my study outcome was at 17 instead of 14. The p-value then is just going to be 1 divided by 200, because I have 200 dots here on this reference distribution. So one of the dots would be sitting at 17 or something more extreme than 17. And 1 divided by 200 is 0.005, I think. It's a pretty small percent. What that means, if the p-value is really small, it means that my study outcome is very extreme in this distribution. So for example, if my study outcome was 20, there wouldn't be any dots out there. So my p-value would be 0. So if your p-value is really small, it means that you're very much an outlier in this distribution. There's some additional comments here, or general comments regarding p-values, and I'll let you read through those. How do we make a decision using the p-value approach? Well, all I need to do when using the p-value approach is just check to see if that p-value is less than 0.05. If it is, then we can say that the data provides enough statistical evidence for the research question. Again, as I said, 14 here sits in that top 7.5% of the distribution. It doesn't sit in the top 5%. Okay, it sits in the top 7.5% of the distribution. So 14 is not enough of an outlier. But if we were way out here at 20, the p-value for 20 would be, I think, 0, right? Because there's no dots out here. And that's going to be very extreme. So I have enough evidence for the research question, or the data provides enough evidence for the research question when that p-value is very, very small. Now, one advantage of using the p-value approach is you don't need to worry about if you're in the bottom 5% or top 5% or the outside 5%. All you need to do is just check to see if that p-value is less than 5%. If it is less than that 5%, then we do have enough evidence for the research question. And if it's not less than 5%, then we do not have enough evidence for the research question. I provide some discussion in the notes about this notion of marginal evidence, so values that are close to 0.05. So that has been discussed by many, and there's issues, I guess, when we start doing things like this. So if we go way back, Brose here discusses some of those issues in that statement. So for us, what we're going to do and what the practice is that 0.05 threshold is very strict. If I'm below that, I have enough evidence for the research question. And if I'm not below that, I do not have enough evidence for the research question. So we're going to be very strict with that 0.05 cutoff here in this class. And that's pretty common practice. All right, so let's look at another example, example 2.1.4. And this is the ear infection example. So my sample size was 23. My parameter value is 50%. The study outcome was 16. Now, what was unique about this example is that it was two-tailed. So in other words, when I'm computing the p-value, I'm going to need to worry about both tails, because the definition of a p-value is values that are as extreme or more extreme that would support the research question. And in this example, both ends of the distribution support the research question. So for a two-tailed test, we need to worry about both the upper tail and the lower tail. So let's talk about the upper tail first. That's easier because the study outcome is at 16. So values that are as extreme or more extreme than 16 in the upper tail are simply going to be 16, 17, 18, 19, 20, 21, 22, 23. How about values as extreme or more extreme in the lower tail? Well, that requires a little more thought. And what I have to do initially is to figure out how far away is 16 from my expected value. So it's about 4.5 away. So my expected value for this example is 11.5. 16 minus 11.5 gives me 4.5. So when I'm determining as extreme or more extreme in the lower tail, I need to go 4.5 away. So another way to think of this is that 7 is the mirror image of 16 on this reference distribution. If I were to take this reference distribution and fold it in half, 16 here would land right on the other side at 7. Now another way of thinking about this is just looking at how far away am I from the edge. So I'm 16 down to 23, or excuse me, 23 down to 16 is 7 away. Well, 0 up to 7 is 7 as well. Now that doesn't work in general. We get into some examples in, I think, Module 3 and Module 4. You're not going to be able to do it that way. So I'd rather have you think about it in terms of how far away am I from the expected value, which is what I have shown here. So the values as extreme or more extreme in the lower tail are going to be 7, 6, 5, 4, 3, 2, 1, 0, going this direction. Now the p-value is that same idea, I just need to apply that in both tails. So for the upper tail, it's going to be the number of dots as extreme or more extreme than 16, divided by the total number of dots. And the lower tail, it's going to be the number of, it's going to be the number of dots as extreme or more extreme than 7, divided by the total number of dots. So here I've obtained a reference distribution. This time I'm using 100 repeated outcomes instead of 200. Again, in practice, we would usually have that number up into the thousands or maybe tens of thousands. I'm just keeping that number low here so we can actually count the number of dots easily. This reference distribution was again obtained under a no difference situation. The upper tail p-value is going to be 1, 2, 3, 4, 5, 6. 6 divided by 100, or 0.06 on the upper side. Those should be turned around there, it looks like in the notes. So 6 is from the upper side, and then 5 is from the lower side. So there's 1, 2, 3, 4, 5 dots out of 100 that are at 5 or below. So the lower tailed p-value is 0.05 from this end. The upper tailed p-value is 0.06. We put those two together for a two-tailed, and I get a p-value of 0.11. So again, making our decisions with the p-value approach, what I need to do, or what the application of the rule is just to look whether or not, or identify whether or not the p-value is less than that 0.05. So our statistical decision for the staring example, that had a p-value of 0.075. Is that less than 0.05? No, it is not, so we do not have enough evidence for the research question. In the ear infection example, the p-value, again, the rule is the p-value less than 0.05. My p-value from up above there that we just calculated was 0.11. And that is not less than 0.05, so again, we do not have enough evidence for the research question. So both in the staring and the ear infection examples, the data does not provide enough evidence for the research question. This comment here just talks a little bit about the fact that we have two different approaches to making a decision about a research question. Okay, we have the cutoff approach where I needed to identify if I was in the bottom, top, or outside 5%. And then I have the p-value approach that I just talked about here, and that is just determining whether or not the p-value is less than 0.05. Now, it may appear that these two approaches are different, but they're not. Okay, so they're always going to produce the same exact decision. And I'll let you read through that comment to verify that. Okay, finally, the last section, writing a conclusion. So this is, in my opinion, the most important step. A well-written conclusion should clearly communicate the findings of your analysis. So the first step in conducting a statistical analysis is the identification of the research question, and the last step is just writing a conclusion for that research question. A conclusion should provide an answer to the stated research question using language that can be understood by the general public. So I don't want you to write conclusions for a statistician, but I want those to be understandable by the general public. So there's three components to a well-written conclusion. The first is just your decision. So identify whether or not the data supports the research question. The second component is just to restate the research question. So the goal of a test is to provide an answer to a research question. So the research question should be restated in your conclusion. And then the third component is to provide a measure of evidence or a level of evidence. So provide the reader with an acceptable measure of statistical significance. That could be a p-value, that might be a margin of error, might be an effect size. Up to this point, we've only talked about p-values. So for now, our conclusions will include p-values. So let's talk about the Parolee discrimination case. So there, the research question was, is there enough evidence to suggest discrimination was taking place against Native Americans regarding parole? The p-value for that example was 0.003. So is the p-value less than 0.05? It is. 0.003 is less than 0.05. So we have enough evidence for the research question. I did not show you the calculations for that p-value here, but we would just need to compute the proportion of dots that were, I believe it was 24 or less. The study outcome there was 24. So let's write the conclusion given that decision. So there is enough evidence. So I have enough evidence for the research question. So that's going to be the first part. There is enough evidence. Part 2 is just to restate the research question. So the research question was asking about discrimination taking place against Native Americans regarding parole. And then part 3 is to provide a measure of evidence or amount of evidence. And I usually just include that in a parentheses here. P-value equals 0.003. So those three components there would make up the conclusion. So let's talk about the staring example. So is there evidence to say that the woman in the study has the ability to identify when being stared at? The p-value here was 0.075. Is 0.075 less than 0.05? No, it is not. So we do not have enough evidence for the research question. So quite simply, the conclusion is going to be, again, in its three components. There is not enough evidence to say that the woman in this study has the ability to correctly identify when someone is staring at her with p-value 0.075. And then the ear infection example is going to be real similar to the staring example there. The conclusion has been written, as you can see here, with its three components. Okay. that does it for Module 2, Part 1, the various elements of a statistical hypothesis test. The next part will include a couple of examples where we go through all of those steps with a new case study. All right, that does it. Thank you.